All right, so let's see, what are we going to do today? Well, yesterday we talked about vector functions, and then we defined vector fields. So vector functions, 8 real numbers and spit out vectors. And then vector fields, 8 triples or doubles or quadruples of real numbers, right? What is so
I don't know,
funny?
it's just funny the way you say it.
Say it?
Say that 8 real numbers and I spit out vector. I don't know, it's just interesting.
Okay, I'm sorry. This is my, in my head, this is how I think about these things. They're little monsters. They eat the vectors and out come the vectors or whatever. Pac-Man, there you go. That's right. Watch me when I eat one of the power-ups and you guys become the blue ghosts.
That's a question. That was my question. Actually, I was in bathroom, then someone next to me, and they're actually.
Did he say he's in the bathroom?
I was in the bathroom. There was a guy actually eating and poop at the same time.
I believe we've hit a new low for any multivariable calculus class at any time in the history of the world. Sweet.
It's so good the camera can't hear us.
Yeah. Okay. No, it
You
can't.
can't be heard on the camera.
Yeah, you can. It was last term when I had the
Yeah.
what was it? The remote
Everything
control
was
in the microphone that they can only hear me. But now this is
Why
like picked up.
Especially
Yeah,
when you're
everything.
so close.
Yeah, so you're feeling a little flatulent. Woo! Okay. Maybe Jeff, you should just cut all this.
Start over.
All right, where were we?
Okay.
Yeah, so
Today.
vector functions. Vector functions took real numbers and outputted. I don't remember. They're vector functions. Okay, so they output vectors, and vector fields could eat things in R2, R3, Rn, whatever, and spit out vectors in Rn. Okay. And so we described a vector field, namely the gradient vector field. And so this is what you get when you take just any a scalar function, you apply the gradient to it. This gives you a vector field. So this wasn't so bad. In fact, it was so nice that we gave a special name to any vector field that comes as a gradient vector field. We call it a conservative vector field. So our first goal today is to find out what,
No.
come on, are the
Okay.
conservative vector fields. And as a tool to finding them out, we're going to talk about 2 very nice constructions. One is called the curl, and the other is called div. Okay. So let's answer this question. What are the conservative vector fields? So let F be a vector field. We're just going to do this on R3. So let F be a vector field on R3. So this means it eats points in space and spits out vectors in space. And now remember, when you have a vector field, just like when you had a vector function, it comes with component functions. So this F, say x, y, z, can be written as P of x, y, z, I, plus Q of x, y, z, j, plus R of x, y, z, k. And remember, these P, Q, and R, these are just scalar functions. They just spit out real numbers, and those are called the components of F. So let's assume that P, Q, and R, and this is a condition we've seen before, have continuous partial derivatives. Okay. This isn't, given the functions that we normally like to work with, this isn't a huge condition. Most of our functions have continuous partial derivatives. Okay. So there's a theorem, and it says that if the cross product of the gradient with the vector field is 0, and I'll tell you exactly what I mean by this in a second, then f is conservative. So conservative means that f can be written as the gradient of little f, for some function f. Okay, so let me explain what I mean by gradient cross product f. So we know that when we take the cross product of two vectors, one of the ways that we can compute it is by using this determinant form, where you put the top row, you put ijk, and then in the middle and bottom rows, you put the coordinates of the first vector and then the coordinates of the second vector. Okay, so the first vector here is the gradient. Well, what does the gradient do? When you take the gradient of a function, what was that?
Partial derivative at x1.
You take the partial derivative with respect to what?
And y and then z.
Yeah, you're right, you do it for each one. The first component has the partial derivative with respect to x, the second has the partial derivative with respect to y, the third is the partial derivative with respect to z. So I'm just going to write down the partial with respect to x, the partial with respect to y, and the partial with respect to z. And I'm not putting the function here. Right? These are just the derivatives themselves. So on the side here, as mentioned, you view delta as that triple. And it's not a vector. And it's not a vector field. Because it's not eating points, this is eating a function. When things eat functions, you usually call them operators. So we're viewing this as an operator. Hello, operator. Give me Okay, so the gradient goes there, and then we can put in f. And what do we put in for f? Well, f is PQR. Okay, so Kaiwei's shaking his head. That's usually a symbol of complete understanding.
I was doing research on multivariable. I was about to do that, I guess.
Oh, you were going to... I'm sorry, am I stealing your final project thunder? I apologize. Okay. So we can compute this just by, well, let's see, what do we do? Remember the determinant, you can use that cross-hatching method. So here we go this way. In the I, you get I, the partial of y, r. So this means you take the partial derivative of r with respect to y. So if I go this way, that's what I do. I take the partial derivative with respect to y of r times I. So that'll be r of y. I don't need to write my partials anymore. I just put it down there. Now the other way I get an I is when I go backwards. When I go I, and then this one, the partial with respect to z of q. But that gets a minus because you're going backwards. So minus qz I. Okay, now for the j, if we go this way, you get positive. So this way you pick up a partial of p with respect to z. Minus, now if you go this way, it's a partial with respect to x of r. So minus Rx, that's J, plus, now for K, when you go this way, you get the partial of Q with respect to X, minus this way, you get the partial of P with respect to Y. That's K.
So P stands for, oh, nothing.
P is this component function. So if F is to be conservative, then, well, that's not correct, what I'm saying. If this cross product is 0, which will make F conservative, then that means that all of these components have to be 0. So if Ry equals Qz, Pz equals Rx, and Qx equals Py, then that cross product is 0 and F is conservative. So you can just check these 3 conditions. This is not the same thing, but those of you in 481 should think, oh, this reminds me a little bit about, like, what? There were some equations like this where you're looking at partials and seeing when they were equal. Highway. Yeah, Cauchy-Riemann equations. Yeah. Okay. So it's a similar sort of thing going on, but these are not the Cauchy-Riemann equations. Okay. So it turns out that this construction, taking the gradient cross product with a vector field, well, it's certainly important in the sense if you're trying to see if the vector field is conservative. But it might not be conservative. But it turns out this is still an important construction even when it's not a conservative vector field. And it's so important that mathematicians give it a name. Well, mathematicians probably didn't give it a name. Physicists probably gave it a name. So we define, put it up here. The curl of a vector field over R3 as the cross product of the gradient with the vector field. Okay, so this is just a definition. Just a name for it. So this is called the curl. Now, note, what is the curl? Well, let's see here. These are functions. You're taking partial derivatives, but you still get functions. And they're functions of 3 variables. So you can feed this thing a point in R3, and these things will spit out numbers times I times j times k, so you get a vector. So it eats an element in R3, and it spits out a vector in R3. So in fact, this is a vector field, again. Right? It eats points and it spits out vectors. So the curl of F is a vector field. So this is always cool in mathematics when you can start with an object and use it to produce another object of the same type that tells you something about the original object. So this curl tells you something about the original object. Namely, if it's 0, then the vector field is conservative. But I mean, this is really a different vector field, right? This is certainly not the same thing. This is not P, this is not Q, this is not R. Okay, so this is not so bad. All right. How about we do just a quick example? So let me give you a vector field. It'll be xz, comma, xyz, comma, minus y squared. Okay. So my question is, can we see right off the bat if this is a conservative vector field? Right. So this says that, well, if this cross product is 0, then it is conservative. Now it doesn't say that if this is not 0, then f is not conservative. Just saying if this is 0, then f is conservative. So we want to check this. Now what does it mean that f is conservative? F is conservative means that there is a function that when you take its gradient, you get this vector field. But when you take the gradient, that means you just take the partial derivative in each component. So that means we're looking for one function whose partial derivative with respect to x is xz, whose partial derivative with respect to y is xyz, and whose partial derivative with respect to z is minus y squared. Now, if you think about that for just a couple seconds, you think, that doesn't seem terribly likely. No? I mean, if the partial with respect to z is minus y squared, then your function is probably something like minus y squared z. But the derivative of that with respect to x is not xz, it's 0. Right? So this is not looking good. Okay, but let's get some more evidence. Let's compute the cross product let's compute the curl. So the curl of f is going to be, well, we can use this formula if we like, or use the matrix. So let's see, it's going to be the partial of r with respect to y, which is minus 2y, minus the partial of q with respect to z, so that's xy, comma, okay, now we need the partial of p with respect to z, that's just x, minus the partial of r with respect to x, that's 0, comma, all right, the partial of q with respect to x, that's yz, minus the partial of p with respect to y, that's 0. So this equals minus 2y minus xy, comma x, comma yz. And this is not 0. Okay. So we have some more evidence to suggest that we can't possibly see this as a conservative vector. Good. Okay. Here's just a little thing I'm going to write down. This is actually going to show up on your homework for you to prove it. So let's let f be, do I need to observe this? No. Little f. So let's let f be a scalar function on R3. So each something in R3 spits out a number such that the second partial derivatives are continuous. Then the curl of the gradient of f is 0. Okay, so this is a homework problem. Now, how does this relate to the theorem? Well, the theorem says that if the curl is 0, then your vector field is conservative, which means it looks like grad f. This is saying if it is grad f, then the curl will be 0. So one says if the curl is 0, then it looks like grad f. The other one is saying if it's a grad f, then the curl is 0. At least if the second partial derivatives are all continuous. So the hint to proving this is the second partial derivatives. Did I say the second partial derivatives are all 0? The second partial derivatives are continuous. Why, in this class, would we care about the second partial derivatives being continuous? We have one theorem right in in the first section of the course that said, if the second partial derivatives are continuous, then something happens. It was a very important theorem for us. Clairaut, exactly. Clairaut's theorem. That's where that condition is going to come into play. So what you can expect is that when you compute things out, you're going to get second derivatives, and that the indices are just going to need to be switched. And you can do that by Clairaut's theorem. And so if you use this example in that theorem, then that'll imply that this f is not conservative. Because if it was conservative, then it would look like grad f. But if it looked like grad f, then its curl would be 0. Then its curl is not 0. So we're okay. Okay. So let's look at this curl a little bit. Now I've written down this operator and this vector field, but they both kind of look like vectors, which is why I could do this. If the gradient cross the vector field is important, what else do you think might also be important? Yeah, the dot product. Right? If the gradient is important, the dot product could be important. Okay. So we're going to define something called the divergence of a vector field. And it's going to be the dot product of the gradient and the vector field. So what is this? Well, let's see. The gradient is the partial of x, partial of y, partial of z. And then the dot product with f, well, that should mean the partial of x, and then you multiply it with the first component of f, which is p. There we go. And then the partial of y times q, and then the partial of z times r. But here times doesn't really mean times. This is an operator. It's supposed to eat it up, actually. So this is the partial of p with respect to x plus the partial of q with respect to y plus the partial of r with respect to z. Or in vector notation, px, comma qy, comma rc. Either way. Well, that looks a lot nicer. What is this? The curl was a vector field again. What is the divergence? Well, let's see. It eats a point. You can put an x, y, z into it. And each of these is a function that will eat an x, y, z and spit out a number. And what do you get? You end up with a vector. Yeah? So it eats a point, and it spits out a vector. And unlike oh dear. I lost track of where I was going to go with this. It should be a number. What's going on here?
Aren't you supposed to
Oh,
just
you know
add
why?
it up?
I don't know why I did this. The I confused the heck out of myself by doing this. There's no I's in here. I just added those arbitrarily. Let's do this again. You do the dot product of these things. that means you do partial x times p, right? Which means partial x of p. So it's just px plus qy plus rz. Those i's were really confusing. They didn't make any sense. Okay, so this is just a sum of functions. So it eats a point, and it spits out a point. So what is it? Well, it eats something x, y, z. Spits out a number. So it's just a scalar function. So, in a little bit, I'll give you a physical reason for wanting to look at the curl and the divergence. But for now, let's just play around with these a little bit. So, let's see. Why don't I take a vector field with continuous second derivatives. Now, what do I mean by continuous second derivatives of a vector field? I mean that the component functions have continuous second derivatives. So p, q, and r have continuous second derivatives. Okay. I really should say this is a vector field on R3. Because div and curl, right, we've only defined these on R3. Okay, so f is a vector field with continuous second derivatives. Why do I want continuous second derivatives? I should say these are partial derivatives, of course. Why do I want continuous partial second derivatives? Try the easy answer. Take back 5 minutes. Yeah, I want to use Clairaut's theorem. Yeah, Clairaut's theorem uses continuous second partial derivatives. Okay, so I'm going to want to use that. Then, what happens if I start with f and I take its curl? Take its curl, I start with a vector field, I get another vector field out. If I have a vector field, I can take the divergence of it. So let me take the div of this. So the divergence of the curl of the vector field. One of the things you do in math, you start defining new things and you realize they can be inputs of each other. So see what happens when you mix them. Turns out, this is going to be 0. Kind of weird. Okay, let's see. So the div of the curl of f. This is, well, you have to take the dot product. By the way, a little mnemonic. Div, d, dot, curl, c, cross. Okay? So a good way to remember that. Cross product gives you the curl, dot product gives you the div. Okay, so first we do the div, so that means we need a dot product of the curl. The curl is the cross product of the gradient and the vector field. Now, this is equal to the dot product of the gradient with, well, the cross product, we've written this down before. It's going to be ry minus qz, comma pz minus rx, comma qx minus py. Now the gradient means you're going to add up what happens when you let the partials act on these components. So the first one is the partial with respect to x. So when you do the partial with respect to x of this, you get ryx minus qzx. Is that right? Taking the partial derivative of this with respect to x. So I get ryx minus qzx plus pzy, because now we're in the y component, minus rxy plus, now we do the z's, qxz minus pyz. Okay, now let's see, ryx, and then minus rxy.
They're the same.
They're the same by Clairaut's theorem, because we have continuous second partial derivatives. qzx with a negative, and qxz with a positive. Okay, those are fine. And pzy and minus pyz. So, you get 0. So this is nice. The divergence of the curl is 0. By the way, we now have 3 very nice things. We have the gradient, grad. We have the curl, and we have the divergence. There is a very popular book amongst physicists who are trying to learn vector calculus called Div, Grad, Curl, and All That. You'll probably find this in the library. Now, I'll warn you though, while I enjoyed reading that book very much, it's really very much a book for physicists. And I'm not a physicist, but yeah, it's different. Okay, so in the first place, the divergence comes from the dot product, but we only wrote that down because the cross product was important. But this here, the fact that the divergence of the curl is 0, tells us, okay, this divergence must be important. We don't know why. We have no idea why, but it must be important. Because the definition is too nice and the properties already are too good. Okay, so we'll come back and maybe see why it is. Okay, so let's see, let's summarize so far. We know that if you take the curl of the gradient, you get 0. Okay, and we're assuming here about continuity of the second partials. If you take the divergence of the curl, you get 0. So we kind of have 3 things going around. You have gradient, curl, and divergence, and things are already looking nice.
So same thing happens if you have curl first and dive second?
Good question. Does the same thing happen if you have curl of the divergence? So, if I asked you this question, it would be a trick question. But you asking me this question is not a trick question, because you're the student and you don't know better. Right, why, so that's a hint as to what the answer is. Why, if I asked you this question, is it a trick question?
Wouldn't it be a vector?
Wouldn't it be, you can do a cross product with scale and a vector.
The divergence, right, is a scalar function. The curl eats vector fields, not scalar functions. So this doesn't make any sense. So that's if you open up nearly any calculus textbook where they introduce curl and div and grad and gradient, they will give you a list of maybe 10 of these things in different orders with some other stuff thrown in maybe to make it interesting. And then they'll ask you, which of these makes sense? Which is not so bad to do, because then you have to remember, okay, wait, which one's a scalar function, which one's a vector field, so forth. Okay. So what can we write down that makes sense? What about, well, we have to eat a vector field with divergence, so what about this? Well, we can compute it. Right, why not? What is this? This is the dot product of the gradient with the gradient of f. Let's do a little work down here. And the gradient of f is just the partial with respect to each component. Right? That's what the gradient does. It takes the partial derivative. Jenna, are you happy about that?
Yeah.
Okay, you look bad.
Yeah.
Okay, now what does this do? Well, it takes the partial derivative of each component when you do the dot product and adds it up. So just takes the second derivatives, all with respect to the respective coordinates, so x, y, and z, and then adds them all up. So the divergence of the gradient of f is actually just f of x plus fyy plus fzz. So what this is sometimes written as is the gradient squared f. Not that it's squaring f, but that you're taking the partials twice. And this, if you just view this as an operator, so this equals the operator where you take the second partial derivative, always with respect to the same variable within that component. And this is so important in physics and mathematics. It gets a special name. So this is called the Laplace operator. And it's related to a very special partial differential equation called the Laplace equation. Good final project topic. Yeah. Isn't that your final project topic? Oh, sorry, that's okay.
He's just stealing everyone's thunder.
I'm sorry. Being very bad.
Was it on mine too?
Hmm?
Was it on mine too?
Actually, you didn't email me yet. She did. She said the Laplace operator,
Also the
Laplace
Laplace
equation
equation.
and harmonic. Yeah.
I said that when we went to the conference and he told me that we're going to do that in class or this and that.
Yeah, but there's a lot more to say about the Laplace equation than I've said. In fact, I haven't even written the Laplace equation down, so there's more to be said. People write dissertations on things related to Laplace and Laplace equations. Okay, so what about the physical interpretation? Of curl and div. Mind you, I'm not mentioning gradient here because we already did the physical interpretation. Remember the gradient said if you were, say, sitting on a hill and you took the gradient to that point, then you take the function, right? Take the gradient to the function and value at that point. What does that tell you? It tells you which direction the function is increasing the most in. So if you're on the hill, it tells you where's the steepest direction to start walking. And the size of the gradient tells you what the size of that, what the gradient is. Okay, so I don't need to do that here, but I do need to tell you what curl and div are. So I'm going to just give it to you in one specific instance. Of course, for different vector fields, they mean different things. But what you might imagine is that you have, I'll say a pipe. You have some nice pipe, and there's water, or some fluid. Could be a gas, doesn't matter. Gases count as fluids, right? Come on, somebody's in chemistry, you can tell me Yeah? Good, thank you. Okay, so you have some fluid, and it's flowing through the pipe. And, well, we're going to make an assumption here, namely that we have steady flow. So steady flow, what I think it means is that the flow through that pipe is independent of time. So that if you took a still shot of the flow at any given time, it would look the same no matter what time you took it. Okay, so at any given point, you can ask, what is the fluid doing? And it has a position vector. And it has a velocity vector. So the velocity vector might look like this at this point. Okay, so it tells you it's going exactly in that direction, and the magnitude of this vector is how fast it's moving. And now maybe over here it's moving down a little bit, and here it's moving like this a little bit. Maybe everything is kind of being forced into the middle. So here it's going like that, like that. So at any given point, you can see what it's doing. And then once you get to the middle, it just kind of goes out in the middle. This point's getting forced into the middle. That's getting forced in. You can see the complication in trying to draw vector fields. Because at every point, you have to draw a vector. Right? Because what does a vector do? It eats a point in space, and it spits out a vector. And I'm doing this in 2 dimensions, but this is 3-dimensional, right? So all these, all the fluid maybe is, I'm trying to get it to suck in towards the middle. Okay? So it doesn't have to do that, but whatever it is, that's what it might be doing. Okay. So the vector field is associated to this picture, right? And we call it V. So let V be the velocity vector field. So by velocity vector field, I mean at every given point, I draw the velocity vector. Okay, so the size of the vector is how fast you're going. The direction is what direction. Okay. So my question is, what is the curl of that vector field? So V is not a vector here; it's a vector field. And what is the divergence? What do those mean? So if I choose a point, x, y, z, so remember curl of V is again a vector field, so it eats points. So if I let it eat a point, x, y, z, so this could be right there, it could be x, y, z. This, well, it spits out a vector. It's a vector field, it eats a point, spits out a vector. And what's that vector? Say it's not this, but it is. A vector giving the axis of rotation. So if you think all this fluid is moving, there's rotation going on there. And it's rotating around, whenever you have rotation, it rotates around some axis. And this vector is going to tell you that's going to be the axis of rotation, right, of the fluid at that point. So this is a vector giving the axis of rotation of the fluid around the point x, y, z. Okay, so you have a vector and that gives you a direction. So that tells you, when that direction is telling you the axis, what else is important? Well, the length of that vector is always important. And the length of that vector is telling you how fast the stuff is moving. So the direction of the vector is telling you the axis of rotation. Tyler?
Is there a difference when you draw a vector? Is there a difference between a straight line or a curve?
So
Or is this
vectors are always straight. Right? So I don't draw curved vectors here. Right? Because a vector is supposed to have a magnitude that is, you're just saying, okay, if I start with this point, I draw a vector, and that tells me a direction. If I curve it, it doesn't mean anything anymore. Right? So this is going in this direction, and then the length of it is telling me how fast it's going. Okay, so let me erase this, and I can say, okay, the vector gives the axis of rotation of the fluid around the point x, y, z, and the length is the, I guess it would be the angular velocity. Is that what it's called? Or angular speed. What is this called? Angular velocity of rotation. So the word curl, you think what's happening is if you have this point, what's the fluid doing? It's kind of curling around. That's where the axis, that's the rotation, right? It's going around it. It's curling around. And how fast is it going? Well, that's the magnitude of the curl vector. Okay, now the divergence, well, this is supposed to be just a function. So it eats a point and it's going to spit out a number. Okay, so I should just get a number out. And that number is going to represent it's going to be the net rate of the fluid that's passing through that point at that time. Okay? Or that is, I feel like is moving away from that point. So there's fluid that is moving away, and there's fluid that's moving toward it. And I want to know what that net rate is, right? In the end, how much is going away minus how much is going in towards it. So this is the net rate per unit volume. Of fluid flowing away from x, y, z. So you pick that point and you say, okay, how much fluid is flowing away from that point? And that's the divergence. And if you think divergence, how much is being diverted away, right, from that point? So that's, I'm guessing this is the origin of those terms, but physicists would know better than I. Okay. So that's one interpretation of these things physically. Okay, so we're going to leave curl and div for a little bit. We're going to end up using them later when we start talking about integrated vector fields. But for now, let me get back to these conservative vector fields for a second and show you just a nice example of these things. So we're talking about Newton's law of gravitation. So this is just, I want to give you one more nice example to have in your head when you think about vector fields. So this is supposed to be a very big planet. And then maybe this is a moon or something, maybe another planet, doesn't matter so much. I know they don't look so big, but you guys are really far away.
Oh, okay.
That's the problem. Okay, so of course, at this point, you're probably aware that there's this force acting on massive bodies called gravity.
What?
This is why you're in college, Janet. You learn these things.
Oh my God.
And Newton was able to derive what is now called his law of gravitation, which tells you the force between them. So whatever that force is, we'll call it F, and the size of that force is equal to, well, let's see, let me call this object O big M, and this will be O little m. O for object, M for mass. It's not a zero, it's just a no. Okay, so this force is the mass of this one times the mass of this one, so it's symmetric, times big G. And if you've taken physics, you've probably seen this before. This is the gravitational constant. This is just a number. 6.634, 637 times 10 to the minus 11s. What is it? Meters per kilogram second squared, something like this.
Something like that.
Meters cubed, of course. Yeah, meters cubed, kilogram second squared, something like that. And then it's divided by, well, I have to give you a number here. Let me. Yeah, in physics they usually use R. Let me use something different. Just for fun, let's assume that this point here is at the origin. We're the center of the universe, that sort of thing. It's okay, you can always set your coordinate axes up so that any point is the origin. So, okay, we'll do that. And so then this point would be x comma y comma z. And I can just go, I think of this as a vector. Right? So this is just the length of this thing, right? It's just the norm of x. And is this right as I've written it?
Mm-hmm. Oh, no, square.
Squared, of course, right? This is the inverse square law. Okay, so this is saying that the distance is more important than the mass. Mass, right? If something gets bigger, there is more gravity. That's short. That's true. But moving farther away is a much bigger deal. So this is the force. What? Okay. And of course, if you like this bit here, this is x squared plus y squared plus z squared. Okay, now I have an arrow going here, but really what I'm interested in right now is, say, the attraction of OM on OM. So the force, right, F is going this way. That's my force. Now, it's very often the case that having a unit vector is important, as we've seen in the past. So what's the unit vector? I really want this going the same way, so I'm put it up here. So this is supposed to be a unit vector. Right, well, the unit vector is in this direction. Well, let's see. If we're going here, the vector is x. Yeah? Unit vector going this way, well, first, a unit vector going this way would be what? How do you get the unit vector corresponding to x? It should be, yeah, you take x itself and divide by its norm. Right? But if I want towards towards OM, I just put a negative out here. That'll make it go backwards. Okay, good, good. Unit vector can be important. So, what is the actual vector field itself? Well, if you know the magnitude of the vector field, and you know its direction, as given by the unit vector, you can get the actual vector field by multiplying its magnitude times the unit vector. So, F itself has to be little m big mg over the norm of x squared times minus x over the norm of x, which is negative mg over norm of x cubed times the vector x. So this negative x tells you you're going this way, and then this is the magnitude of the force. Okay, good. This is, of course, called...
Was it really?
Yes, it was the original thing that you have to show that this is equal to that.
gravitational vector field.
And I could not get it. That makes two of us.
Now why is it a vector field? Well, you put in a point, and that determines what this x is. Okay? And that's a vector. So you put in a point, and you spit out a vector. So this is a gravitational vector field. So we can write this out in real gory detail if we like. But I don't want to.
Did you want to look at it? Did you want to look at it? No.
But here's something neat. If you take the curl of the gravitational vector field, what do you think you get? Well, there's only one possible answer could be if I said, what do you think you get?
0.
Yeah, okay. It turns out that you get 0. The calculation is not hard at all. You can do this on your train ride home or something. I mean, it won't take you long. So the curl is 0. And if you take the component functions, and it's easy to figure out the component functions, right? The x hat, when you take its norm, right? This is just the square root of x squared plus y squared plus z squared. Right? That's what the norm is. And then you raise it to the 3, so it's actually x squared plus y squared plus z squared to the 3 halves. Okay, so that's what the component function is going to look like. Fine. Computing the curl is just a little formula. You just take some partial derivatives. And you'll see the very first one is 0, and then you'll see, wait a second, this problem is completely symmetric in x, y, and z. So the other ones must be 0. It's not hard. Not only that, but as long as you're not at the point 0, 0, 0 itself, all these component functions have continuous partial derivatives. Right? They're all going to, the only problems are ever going to be at 0 from here. But assuming you're not at 0, so away from 0, the components have continuous second partials. And so, well, what do we know? If you have continuous second partials and the curl is 0, then f is conservative. So this is cool. Newton's gravitational vector field is a conservative vector field. This, you can check the curl is 0. Well, that means that there is some function f such that big F is the gradient of little f. Okay, but that function isn't hard to find. So if you let f of x comma y comma z be this function, then it's as easy as taking 3 partial derivatives. The gradient of f equals the gravitational vector field. So you can actually find that. So this is useful. Physics, of course. I think we should stop here. Oh wait, is that how I forgot. How close is that?
It's the same. It's the same.
Oh.
How you figure it
Oh,
out?
okay. Is that the right time? Okay. Now let's stop here. Our next order of business is going to be to take vector fields and do the one thing we haven't done with them. We haven't integrated over them. Okay, so we want to integrate vector fields. This is going to force us to go back and actually do something a little bit easier first, which is just integrating normal functions over balling. Say you have a function of 2 variables, f of x, y. Instead of integrating over a line segment, we're going to integrate over a path, right, or a line. And it looks something like this. And when we integrate over it, we're going to get something called the line integral. So we'll have to define what a line integral is. Those of you in 481 have seen this, and there will be a lot of things that look very familiar. It says the same thing. And then we'll use that to build up the line integral enough that we can talk about integrals of vector fields. And then things are really going to get cooking.